So the question is, what's the significance of the charge to mass ratio? Anybody know? Dylan? The charge to mass ratio. Now, when we did the cathode ray experiment with the magnet, and we showed that what was coming out of the magnet had an effect on the electrons. Is everybody clear? Well, there were some people, there's always skeptics. So there's some skeptics that asked JJ, they're like, JJ, you know, what about the nonmetals? We know that electrons are coming out of the magnet, which is a metal, but what about the nonmetals? Are you sure electrons are on everything? So he's like, oh, I guess I got to prove that to you too, because you know how some people are, they just won't accept, like, unless it's proven. So they're like, well, we don't think it's in everything, you have to prove that. And that's when you see the charge to mass ratio coming into importance. So if you remember yesterday on the video, they showed you that they put a gas in the cathode ray. So I've got it up here, I froze it, so we can go back to the video and see it, where you can see that the gas is actually in the cathode ray. So we had to build a new cathode ray, which is different than the one we showed in class, the one in the textbook. This is the complicated one. And what he did, he stuck many different gases in there, like oxygen, nitrogen, and then he showed that for every gas, the charge to mass ratio is the same. Now, what does that mean, the charge to mass ratio is the same?
That there's electrons in everything.
Okay, what'd you say?
Like there are electrons, whereas they thought there wasn't.
Okay, so in the nucleus, what is associated with the mass? We've been learning about this. What in the nucleus is associated with the mass? The protons and the neutrons, right? You said neutrons, which is correct, but there's two of them. So we've learned that for every element, they have this equal number of what? Protons and electrons. So that's what's the same. It's very important to understand that the protons and electrons are same. That's the only way the charge to mass ratio would be the same. In order for every element to have the same charge to mass ratio, which is this right here, they'd have to have the same number of protons and electrons, because the protons would be the mass and the electrons is going to be associated with the charge, right? So for them all to be the same, they'd have to have equivalent, they have to be balanced. So for this number to be the same for all of them, does that make sense? They all have to have the same charge? Yeah. If they all have the same charge, which is 0, they're all going to have the same charge to mass ratio. So then he's like, look, you know, if metals have the same charge to mass ratio, then the gases will as well. The charge there is representative of that. So he's able to prove that all elements have electrons in it. That's pretty complicated. I mean, for him to come up with an experiment like this back then and to be able to do the math as well, shows that they were very intelligent. Proton plus electron equals neutron. And we talked about how that the electrons are just traveling so fast, which is why you don't have all neutrons. Like if you took a magnet and you threw it at your refrigerator, it's going to bounce off. But in a star, if it collapses, it kind of condenses the movement, so you can form a neutron star. You remember going over that? So neutron stars are possible. Does that make sense? All right, so now we're going to look at star formation in stars when we get into chapter 24, which is like nuclear, because that's where all the fusion and fission happens, so we'll bring those up there. But when we look at what equals one atomic mass unit, the atomic mass unit is associated with, what did Kai say? What is one atomic mass unit?
Neutron.
Right, one proton is equal to one neutron. That is atomic mass unit. Now, this is a little bit tricky because you're thinking to yourself, well, if they're equal, this math right here says they're not equal. Does everybody see this math right here? It says they're not equal. And now down here you're saying the atomic mass unit is equal. So you're like, well, what's going on with that? Well, an electron is only like 1/1800th of a what is it, like a proton? So it's a very small amount. And they're saying, well, it's just so small, it's negligible, it's not going to... The mass of the electron is not included in the mass in the periodic table. So that's kind of how they're getting away with it. Even though it's not exactly equal, these two are not exactly equal. A proton is not exactly equal to the neutron, is everybody clear? We're just kind of like estimating a little bit. I know math people struggle with this. They're like, what? You cannot estimate. It has to be just a little bit, you know, bigger or a little bit smaller. Okay, yeah, that's true, but you know, for the purposes of measuring things in our world, we're just going to say they're close to being equivalent, even though they're not. Everybody clear?
So is it like equal in number or equal in mass?
Well, they're saying it's equal in mass, even though it's not. Okay, this one is a little bit, the proton is a little bit smaller. So this one's a little bit smaller than this one, because we're showing you here a proton plus an electron equals a neutron. Yeah, the electron's the smallest part, because you see the little piece right there? Yeah, it's kind of like, you know, in Pac-Man, you got the little dots. The electron would be the dot, Pac-Man would be the proton.
Okay, so do all protons and all neutrons weigh the same?
No, the proton is going to be a little bit lighter. But for the purposes of science, we're going to say they're equivalent, because it's very close. Our scales that we use in the lab are not really going to pick up the difference. So for practical purposes, they're pretty much equivalent. But for nuclear purposes, they're not. But most chemistry is not nuclear. Most chemistry in the lab is all electron-based. So it's not going to make that big of a difference to us in the laboratory. So we can just say they're equivalent. Now, we shifted, if you remember, Dalton had his atomic mass unit based on hydrogen. So we go back to, you know, our periodic table, and we look at Dalton. He was the one who said, well, let's base everything on hydrogen. You see how hydrogen has a 1 there? Everybody see the 1 there for hydrogen?
Yes.
And we shifted away from hydrogen. Why did we go away from hydrogen?
Unstable.
Because it is starts with a G, a gas. So we don't like gases that are moving around. And not only is it a gas, it's diatomic. That means there's 2 of them. It's like H2. And it's moving around. So they prefer to use what element? Carbon. Yes. And when we say, you know, what equals 1 atomic mass unit, they'll say 1/12 the mass of carbon-12. Because there are 6 protons and 6 neutrons. So that's really kind of where we are today with isotopes, right? So in order to find the number of neutrons, what do we do again?
Protons plus electrons.
Right, but how would I find the number of neutrons if I had like carbon-12 here? What would I do? I would take 12 minus what? 6. So it's the mass minus the protons equals the neutrons. Is everybody clear there? So this one has how many neutrons? It has 6. Now let's look at the next one. We have 13 minus 6. How many does that have? 7. Now let's see the last one. 14 minus 6. How many does that have? 8. So did everybody see up here, all isotopes have the same what?
Number of protons.
Number of protons. Very good. That's how you know it's carbon. And then all isotopes have a different number of neutrons. And that's basically the lab we're going to do tomorrow. You can find the percents of this. Like you have in the universe, a lot of scientists think that different places have different, I guess you would say, percent abundances based on when the particular solar system was formed. Because you can have different half-lives, so you could have different abundances. So you have to keep that in mind when you're looking at, let's say, material coming from another location. The percent abundances could be different because when we look at radioactive decay, half-lives, the percent abundances might not be the same. We don't know that for sure. It's still speculation. We haven't proven that because we haven't been very far out of our own, like, solar system. We sent, the Voyager 1 to Proxima Centauri, and it's not going to get there for like 60,000 years. So there's a lot of stuff floating out there in our own solar system. It's hard to tell. It's kind of like when Claire Patterson was trying to define the age of the Earth. He had a lot of lead that was interfering with his experiment, and that would be lead that humans have created and put in the atmosphere. So he was trying to date the Earth. We'll talk more about that later. But when you deal with contamination, you don't know for sure what your data is saying. Contamination is a big problem.
What method did he try to use?
He used uranium. Regardless of what gas J.J. Thomson put in the chamber, he got the same charge to mass ratio of 1.75 times 10 to the 11 coulombs per kilogram. So coulomb is just a charge, kilogram is a mass. So if you didn't know that, you know it now. Do you have to memorize it? No. We're just trying to explain to you that he had to prove that electrons were associated with other substances besides magnets. He showed it in a magnet, but how do you know it's in all of the atoms? So if the charge to mass ratio is the same, what does that mean? What is the mass composed of in the atom?
Protons and neurons.
Protons and neutrons. And what surrounds the atom? Electrons. So all elements have what charge? Neutral. So they all have the same number of electrons as protons. So if all elements have neutral charge, then all elements should have the same charge to mass ratio. Does that make sense? I mean, the charge to mass ratio should be the same if you change the number of neutrons or protons and you have the same number of electrons, right? The mass is going to be different and the charge is going to be different because you have a different number of electrons, right? So he ends up proving that if all elements have the same charge to mass ratio, then they have to have electrons in their structure. That's all he was trying to do, is just show that electrons were in the structure. He didn't know where they were, plum pudding model, they're just all over the place. The electron made the neutron, remember that? And which one is larger? Yeah, the proton's larger than the electron, and you add them together and you get this neutron. So which one should have a greater mass? The proton or the neutron, which one should have a greater mass? Neutron. Yeah, the neutron. So if you look in your book, it shows this on page 114. So if you turn to page 114, you'll see that the actual mass of the proton is 1.673, and the actual mass of the neutron is 1.675 times 10 to the negative 24th. Does everybody see that? So the neutron is just a tad bit larger. Now, when we look at question, or bellword number 2, what equals 1 atomic mass unit, we do a little bit of estimation in chemistry. And we're going to say that 1 proton equals 1 neutron as far as the atomic mass unit. Even though they're not exactly the same, we're just going to, for the purposes of chemistry, that is in the lab, most of what we do in chemistry is electron-based. It's not proton and neutron-based. just because when you get into nuclear chemistry, it gets dangerous and you have to have more advanced equipment. And most of the things that are bought and sold are electron-based, like pharmaceuticals and just equipment, cell phones. Those are all electron-based magnets. So we're just going to assume that they are equivalent, even though they're not. Is everybody clear? So in the back of your mind, just remember, they're not totally equivalent. Now, if we went back to Dalton's list of substances, you remember that? Dalton's list of substances? He had hydrogen at the top. So what was he considering hydrogen to be? What was Dalton considering hydrogen to be here? The atomic mass unit. 1. You typically make atomic mass units by taking the smallest thing and dividing by itself. We do this quite often. We do this to help solve for ratios, like water, H2O. If you're given different quantities and you want to know what the formula is, you divide by the smallest to give you a whole number. So the atomic mass unit here is hydrogen. Now it's not currently, hydrogen is not used. Why don't we currently use hydrogen? It's a gas. It's diatomic. It's floating around, moving all over the place. So we don't like it for that reason. So what do we currently use? What is the element that's currently used for the atomic mass unit?
Carbon 12.
Yeah, carbon-12. And why do we use carbon-12? Backbone of life. Carbon's the backbone of life. Even though oxygen doesn't have any radioisotopes, carbon's still used.
Foil of beryllium. The beryllium foil emitted the mysterious neutral rays. Chadwick placed a target in the path of these rays. These rays knocked
H divided by E from 1. Substituting in this equation, we get y equal to E by 2m.
In 1935, Chadwick's received the Nobel Prize in Physics for providing the existence of neutrons.
Remember Voyager 1 said in there it's going to take about 60,000 years to get there. When we look at the masses on the periodic table, it's associated with the isotopes in our solar system. We don't really know if they're the same throughout the universe because different solar systems have like different bursts. And when you have different bursts, you're going to have like different isotopes because they have different half-lives. As you're living, you're taking in carbon-14. When you die, you stop doing that. So the question is, if you have an earlier, let's say, solar system, is it going to have the same masses as we have here on the periodic table? We don't really know that. That hasn't really been proven yet. The thought is that they don't. We don't have really enough data from those rocks to prove it. You can look at like visual spectrum things, but it's hard to know if that's like actually inside the rock. Because usually when we do our analysis, it's going to be based on, you know, not just gases like J.J. Thomson did. He used a magnet as well. This is true when we talk about aging the Earth. We'll talk about that when we get into chapter 24 and how there's a relationship between what I just discussed and the age of the Earth.